Hello, welcome to section 1.5, infinite limits. Infinite limit would be a limit in which f of x increases or decreases without bound. So as you approach a certain x value, it's going to shoot up or shoot down. So definition of infinite limits: let f be a function that is defined at every real number in some open interval containing c except possibly at c itself. The statement, the limit as x approaches c of f of x equals infinity, means that for each m greater than 0 there exists a delta greater than 0 such that f of x is bigger than that m whenever 0 is less than absolute value of x minus c less than delta. Similarly, the statement, limit as x goes to c of f of x goes to infinity, means there's for each n less than 0 there's a delta greater than 0 such that f of x is less than that n whenever 0 is less than the absolute value of x minus c less than delta. So to define the infinite limit from the left, replace the 0 less than x minus c less than delta by c minus delta is less than x less than c. To define the infinite limit of the right, replace this expression 0 less than the absolute value of x minus c less than delta by c less than x less than c plus delta. This delta stuff, don't stress about it. This is the purest definition of it. So I realize not everyone's going to be utilizing that. Don't stress. It's okay. Let's make this a little more concrete. Determine whether f of x approaches infinity or negative infinity as x approaches negative 2 from the left and the right. So as we see, where is x plus 2 0? That's where x equals negative 2. So we have a vertical asymptote at 2. Negative 2, I should say. So the way this graph is going to appear, as you approach it from the right, it's going to get up, 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 up like that. From the left, it's going to go down. So our limit as x approaches 2 from the right side, that plus, remember that from 1.4, of 1 over x plus 2 is going to be infinity. Whereas the limit as x approaches 2 from the left side, we're talking about this case, of 1 over x plus 2 is going to be negative infinity. So you might recall what the vertical line the graph approaches is called vertical asymptote. Hopefully you remember that from Math 126. Vertical asymptote, the vertical line of a graph approaches as the limit goes to infinity or negative infinity. A definition of a vertical asymptote: if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph. And we find this places that the denominator would be 0, give us vertical asymptotes. Let's go on to the next page. Okay, vertical asymptote, let f and g be continuous on the open interval containing c if f of c is not equal to x. Actually, that's correct. And g of c is equal to 0, and there exists an open interval containing c such that g of x is not 0 for all x not equal to c in the interval. Then the graph of the function given by h of x is f of x over g of x has a vertical asymptote of c. The whole point of this, wherever your denominator is 0, you'll have a vertical asymptote at that point. So we're going to find the vertical asymptotes for example 2. I'm going to scroll this up, get both 2 and 3 down here if I can. So where do we have vertical asymptote? Well, it's where the denominator is 0, and the denominator in this case, f of x equals 1 over x squared. X squared is the denominator. So we have x squared equals 0. That's where x equals 0. So our vertical asymptote is that x equals 0. In the next case, h of x equals x squared minus 2 over x squared minus x minus 2. This is x times x minus 2, over x minus 2 times x plus 1. Oh, that's not 2x. I'm sorry. I thought I was going to have a 2x there. So just x squared minus 2 on top. Nothing's going to factor in the numerator. We can't cancel. So where's x minus 2 times x plus 1 equal to 0? That's where x minus 2 is 0, or where x equals 2. X plus 1 equals 0, or where x equals negative 1. So our vertical asymptotes are going to be at x equals 2 and negative 1. For the next one, we have f of x equals x over x squared plus x minus 2. That's x over x plus 2 times x minus 1. So we set the denominator equal to 0. That's where x plus 2 is 0. X minus 1 is 0. So our vertical asymptotes are going to be at x equals negative 2 or 1. Okay, feel free to pause if you need to. I'm going to go on to the next example. Find the limit as x approaches 2 from the right side of x minus 3 over x minus 2, and I put this in the calculator. For 2.2 we have negative 4. For 2.1 we have negative 9. For 2.01 we have negative 99. 2.001 we have negative 999, which leads us to conclude this is getting more and more negative going further down. So the limit as x approaches 2 from the right side of x minus 3 over x minus 2, is going to be negative infinity. We'll go on to the last example, last page. Properties of infinite limits. Let c and L be real numbers, and let f and g be functions such that the limit as x goes to c of f of x equals infinity, and the limit as x goes to c of g of x equals L. Sum or difference, the limit as x goes to c of f of x plus or minus g of x is infinity. Product, the limit as x goes to c of f of x times g of x is going to be infinity. That's because the f part's infinity. And then quotient, limit as x goes to c of g of x over f of x is 0. So if we divide a constant by infinity, we get the 0 in the limits. Example 5. Find the limit as x goes to 0 from the left side of x squared minus 1 over x. This would be like finding the limit as x goes to 0 from the left side of x squared minus the limit as x goes to 0 from the left side of 1 over x. So here we get 0. Here we get, it's from the left side, so it's going to negative infinity. 0 minus negative infinity is just infinity. And that'll do it for 1.5, infinite limits. Hope you enjoyed that. So send me your questions. Thank you.